thinks that you can put mass in a way that it does not obey the Pauli exclusion principle, and then it behaves in a strange way because all the mass uses the same space, and so it's not mass itself what makes the difference. In fact, it's another property that it's called the spin. It's called the spin.
It's not spinning.
But it's not directly spinning, as if it was spinning around itself.
Interesting.
¿Hacia qué lado?
Sí, se me continúa. Creo que fue demasiado.
¿Los dos?
Sí. Like I told you, like I did my research, and there is a lot of information, but I think it's already for someone that already has an idea or some scientific background. For people like us that don't really understand much, I think it's hard to understand. It's hard to put the head around it.
Well, yeah, I mean, I am now working with much bigger molecules than these ones here. So now I mainly work with biomolecules with proteins. So I'm studying different biological process at the molecular level. So smaller than a cell, but at the level, but much bigger than an atom, because proteins are made of, I don't know, maybe 10,000 atoms or something like that, or maybe more, or probably more. So you cannot go into the detail of what is doing every atom itself. And we are working in studying, for example, what is the mechanism of, at a very basic level, and many people are working on this, so we are not alone, but for example, on how the proteins that are responsible for Parkinson's disease cause the aggregation that ends up killing the neurons that cause the disease, right? But this process starts because one of the proteins that is called alpha-synuclein behaves in the wrong way, you know? And why it behaves in the wrong way and how
You can't address it.
we are trying to understand this.
Wow, that's so interesting.
But we are also working, for example, in trying to use you know that insects communicate between themselves by sending molecules that are called pheromones.
Oh, I didn't know that.
Yeah, so for example, a female insect sends a compound to attract the males, especially, for example, for nocturnal species, but for many of them, because males cannot otherwise find the female form. And so,
how do they do that? They just
yeah, in fact, people say that even humans have some kind of pheromones, or
yeah,
if you think about it,
if we do the same.
well, at least we use artificial pheromones when we put on a perfume. Yeah.
Sorry.
Yeah.
Every people has their own smell.
Exactly. You could probably recognize members of your family by your smell. So
Sorry.
that's okay.
So now, if you grab the little
Yeah.
box.
Where is it?
Back in Argentina, I have a friend that was studying how to take the sunlight and make it energy.
Yeah. We could ideally, 100%, but it's very difficult. Yeah. Plants don't take it either 100%,
Yes.
but they are quite efficient. I think more efficient than our plants. But they had millions of years of evolution to
genetic information.
to optimize the process.
Yeah. Do you hear my voice? All right, we are ready then. I told them, by the way, because they're just being very nice to help me, if they feel bored, they can like go and, you know, so just if they leave, so you know. I mean,
it's okay.
for us it's bad because like maybe that, but if they want to go to the bathroom, sorry, no. No, I said it, everything. I'm going to have the questions here, but I think what I really like about one of the things about my show on YouTube is that I really like to improvise. So is it okay if we don't go through the questions? Okay, all right, because I prefer like that. But you know more or less what I'm looking for. I think I already told you. But okay, so one thing I have to do, go. Yes. I think it's recording, no? Check. Is the red thing there?
Yeah, it's recording.
Okay, yeah, the clap. 1, 2, 3. Okay. So now we're ready. All right. So thank you so much, Ramon.
You're welcome.
I think we're going to do, like I said, a little bit in English, then a little bit in Spanish, and a little bit Catalan, because I promised Alejandro to promote a little bit also the Institute and to thank the Institute for the opportunity. And first, can you please explain what we have here and what are the differences?
Yes, okay. So these are models of molecules.
Okay.
And molecules are composed of atoms, and each of these spheres represents one atom. This thing represents a bond between the atoms, which would be created by the electrons that each atom have, that are shared between these two atoms. But here you could think of these small molecules, the small points, as only representing the inner part of the atom, like the nucleus.
Okay, so we can think that this is the nucleus and this is the electrons, and this is another nucleus.
Yeah, but in fact it's more like a schematic representation, because the electrons are all over, and this is what is shown here. Oh. So here these balls would represent like the real size of an atom, which comes from the electron cloud around the nucleus. So the nucleus is much smaller. It's like a small ball in the middle of a field, and the rest are the nucleus. Or in this star galaxy analogy, the nucleus would be like the sun, and the electrons would be like the planets orbiting around the sun.
Okay. And if the nucleus was in here, inside of here, it would be like a very small thing?
It would be tiny.
In here, like in the middle?
In the middle of each of these balls.
Okay.
And then because the balls are bonded, they are overlapping. That's why you don't see like two spheres, but they are overlapping.
Can I ask something? How did they bond? Like how are they, like
atoms bond by sharing electrons, right? So,
so is this an electron? No.
This would represent like all the electrons of this atom, which would be like 6 or 10.
Okay.
But the electrons in their world, they follow the quantum physics rules, and it means that they are not orbiting like planets with defined trajectories, but they are. You could think of them as being in a cloud or a mist. So they don't have like a defined positions. They are like a cloud floating around the nucleus, but they are moving very fast. So it's not like a cloud, like a static cloud where the droplets are like, when you see the fog, you see that the droplets are moving very slowly. In fact, the electrons are spinning super fast around the nucleus. And then when two atoms get in contact, if they can react chemically, they will, and this depends on how many electrons they have, they can share these electrons, so that the electrons do not belong to my cloud or your cloud anymore, but are in between. And this sharing of electrons makes a chemical bond.
And it's in the empty space?
It's in the space between the two nucleus, and it's represented here by this line. But this is only a representation, because the result, the electrons are all around both of the atoms, right?
Okay, yeah.
But they create like a force joining them. Like if we had like a spring between you and me, a very stiff spring, because bonds are strong. And this is what is represented by this line. So this line represents more the concept of the bond. It's not that the electrons are only here, right? The electrons are all over here.
Oh, okay.
But the result is that these two atoms being chemically bonded means that they will be together.
So there's a lot of this here, like millions of, like this, like
No,
this
no,
here,
no.
here.
Sorry, I didn't make myself.
This, all the way to the
No.
other nucleus.
Sorry, this, or maybe, can I move it? Yeah.
Oh.
This would be representing one of these small balls.
Oh.
But this small ball is just simpler to see where it is and what it is connected to, that if you put it with its real size. So the real size of this ball would be like this. Well, not real in this model, right? At this scale. So the atom would be like this. So the electrons would be like we have here. But here, it's harder to see that this is bonded to this and that there are 6 atoms here. Would you have guessed that there are 6?
No, never.
Whereas here you can very easily count them.
Okay. I think.
It's not the same molecule, so these are 2 different molecules.
Okay, yeah, that for
That is
sure.
clear.
Yeah.
But this black kind of, they are not balls, but parts of balls, of spheres, would be like these black ones. They are carbon atoms. We always represent them as being black.
Okay.
But here is how they really look. So they are, the electrons of all of them are together, shared, and they create like this common shape, this common cloud.
Okay.
But this is hard to...
So the electrons are kind of like protecting the nucleus.
Yeah.
A little bit. And how do they, because you said in the beginning, my question is, so where is the empty space here? So if this was one nucleus, and if this was the electrons and another nucleus, where's the empty space? Because the empty space
because the empty space is like a paradox.
Is it not real?
Well, it depends on how you define empty. It's a bit like what we said before. Empty is when you cannot interact with something. You don't not see it. Like this room, from here to that whiteboard, it's empty for me. But there is air, I know. But it looks empty because I don't see the air, I don't feel the air, I don't interact with it. See?
Yes, true. Yes.
Agreed?
That's what he said when we were waiting for you. Actually, yeah.
And then if I were, and so the electrons are like small negative charges. And the nucleus is a positive charge, or larger positive charge.
So that's what does the...
That's what holds electrons close to the nucleus, orbiting around the nucleus.
Okay.
And that's what makes also chemical bonds, because then some electrons can be shared between several positive charges, which are the nucleus. And that is more stable than each nucleus having its own set of electrons. But
so that's where the protection comes from.
Yeah, so in that sense, there is nothing, or there are just, electrons are like points almost, so they don't have size.
Okay.
And the nucleus is also very small, much larger than an electron, but still very small. So there is nothing there almost.
So the representation being a circle is just so it's easier for us, because
no,
they're
because
not really a circle?
They are, that cloud where they are orbiting has like a spherical shape. It's close to a sphere.
You can see in the microscope that. Oh, okay.
And you can calculate it, and you can see that they are very spherical.
Oh, okay. So this has a reason.
Yeah.
Okay.
But then, so in that sense, there's almost nothing. But in reality, there are very strong interactions, very strong forces between electrons, which have negative charge themselves, and electrons within the nucleus, which are attracted very strongly. Okay. And that's why this table is made of electrons. My hand is made of electrons, and I cannot go through this table because electrons in this table repel electrons in my hand. Oh. In fact, the nucleus are not felt because the nucleus are so in the middle of the atom
So a nucleus and another nucleus could never ever touch each other.
No, that's when you have like
Big Bang.
in the sun you have nuclear fission, nuclear reactions. Then two nucleus come together and form a new nucleus.
When the light of the sun comes?
No,
or in the sun?
in the sun itself. That's
what
where
happens?
the energy from the sun comes from
I didn't
nuclear
know that.
reactions. Yeah.
Oh, wow. Sorry, as you see, I know nothing. Like
But,
I feel really...
And in fact, you know that there's this project of creating this new source of energy from nuclear fusion that Europe is trying to develop, and also United States, and so because
you take the electrons away.
Yeah, you give a very strong energy to the nucleus, so that the electrons get separated from the nucleus, and then but still two nucleus are positive charge, so they repel each other. So you need to give them a lot of energy to merge into another one.
Oh, I think I saw a machine once on YouTube that is like, I think one guy in Russia in 1980 something was caught up in a machine, and then he didn't die. They don't know how, but he has several damages to the brain because it was such a high
There's a lot of energy.
voltage of energy. So if we can do that, what does that mean for the energy of? So if we can repel that energy and the nucleus meet,
when they meet, that releases a lot of energy, and that is
so much that could power like Barcelona.
That's what powers the sun.
Oh wow!
So that's what, yeah.
But the sun is like billions of them, no?
Of course, yeah.
Okay.
But if we could, if we could recreate, we have recreated that with single atoms. But of course, one atom doesn't give us enough energy. It gives a lot, but an atom is very, very, very small. So.
So one atom, just to give context, how much energy could it charge a phone? Or
no. But to give context, like in a glass of water, there's the number of atoms that are there. I don't know how to say it in words, but it's larger than a billion, right?
Okay.
So it's around at 1 followed by 23 zeros.
Ooh.
That's the number of atoms that are
in one. Wait, do we have one? Just so we. This could be a glass.
Yeah, more or less.
So, sorry, pardon. So in here, there's 20. I'm gonna say like this, even though it's wrong. 23 billion zeros.
No, there are a 1 followed by 23 zeros
of
atoms. More or less.
Okay. All interacting at the same time and all doing the repelling of the electron, negative, positive.
Yeah.
Okay.
In fact, that's what I was explaining before.
Sorry, if you want to drink.
I was lying when I said that electrons repel each other because they are negative charges. This is true, but this is not the fundamental reason why this table is not transparent to me, why it feels solid. It feels solid because electrons are a kind of particles that follow one quantum property that we do not see in our macroscopic world. And this property is called, well, we don't see it. We cannot isolate it. We see it in everything we touch and we interact with. And this is what is called the exclusion principle, Pauli exclusion principle, which says that no two electrons can be in the same place at the same time. And that's why if there is an electron from the table here and an electron from my finger here, my finger cannot go through the table because the electron in the table says, hey, no, this is my space. Right? This is my place. And there is, so in that sense, atoms are full. There's no room for any other electron there, right? You can, if you have an atom, this is a carbon atom of 6, there are 6 electrons around it, and you cannot put a 7th one in between. There's no way it can go there.
Okay.
So in that sense, it's not empty, it's completely full.
And one question. I have 3 questions, but
But you could put another type of particle, because this exclusion principle is only between electrons or between the same type of particle, right? So at the end, this is what was trying to explain before, and I let you ask the question. At the end, being full or empty depends more on the interactions you feel than in the things that are there. So if you don't interact with what is around you, it feels as if it was empty. So if I'm a photon of light, I can go through the atom, and it's empty for me. But if I'm an electron, when I reach this one, it will say, hey, this is my place, and then I have to rebound, and it's full.
Wow, so light doesn't enter the physics law of the electrons.
Sometimes it interacts, that's why it's green and this is black, and so it interacts with matter and we see it differently, but many times it goes through.
Wow, so the electron lets it pass.
Yeah.
And it lets it touch the nucleus.
It doesn't see it, literally, it's light, but it doesn't see it, it doesn't interact. The photon does not have an electric charge.
Because it doesn't feel like it's going to be, maybe it doesn't have to protect the nucleus.
Yeah,
Going back to, sorry, for me it's easier to understand like that. Could it be that, or do you?
Yeah, it's like, I mean, electrons and neutrons have electric charge, positive and negative, whereas photons don't have charge. So they don't have charge, they don't see anything with charge, they don't care.
And is it, so it's impossible to, an electron can never exist without the nucleus. It doesn't exist.
No, you can, given enough energy, you can take it out of the nucleus.
Yeah, but we can do it, like in the universe, like.
Yeah, we can, yeah, I mean.
Does it exist without a human interaction?
Yes.
Doing that?
Without human, well, for example, if the temperature is high enough, temperature in fact is how fast things are moving at the molecular level. And so in the sun, where the temperature is very high, thousands of degrees, atoms or would-be atoms are moving very fast and colliding with each other. And in these collisions, electrons come off. And in fact, the atoms in the sun, you don't have atoms like a nucleus with electrons around. You have nucleus and electrons all over the place.
Oh,
like a
chaotic.
Mess. Chaotic, yeah.
Oh, wow.
And that's what allows the nucleus to come together and to fuse. So it happens. But it also happens, do you remember the old TVs that had like this, they were called cathode tubes?
Yeah.
And they were like gray when there was no signal. And
yeah.
Well, that was, what creates the signal is electrons traveling and hitting the screen. Free electrons.
Oh, that they're not.
Without an atom.
They're not part of an atom.
They were part of an atom at the one end of the TV.
Oh, and then
then with a strong, because they are electric charges, so with a strong electric field, you can pull them out of the atom, and then they travel free until they hit the screen and they create a movie.
Wow. So a movie. Sorry, for me this is super interesting because I'm from the movies. So a movie is the only, when you actually see a movie, you're only seeing a reflection of an electron.
You're seeing
the screen.
When the electron hits the screen, it creates a photon, which is what you see. It creates light.
Okay. Wow. So you're not seeing atoms.
Well, the process of seeing
in the screen, yes, but not in
the process of seeing, so our eyes are only sensitive to photons, to light. This is by definition. So you can only see light. You cannot see anything else. No, because you can see where light comes from.
Yes.
But what you see is the light, not. So you don't.
But there's a difference. I think my question is, there's a difference. Then we cannot see it, but there's a difference to this table, what I'm looking at this table, because it has atoms, rather than what's being screened there because it doesn't have atoms, right? If I understood what you said, right?
Okay, yeah.
Do you understand my question? So this has an atom and a nucleus and all the composition normal.
Yeah, I understand.
But the projection doesn't.
In fact, everything is made of atoms, except for everything is made of. But what you were seeing there, in fact, was like an atom of the screen. This is not the real example because that screen is too new and it works with LEDs.
Okay.
And
too modern. Okay.
And that's why it's flat. It's not like with the old ones that have like that tube, because that tube was like a cannon to throw electrons, literally.
Oh, wow. Okay, so only in that moment.
Only in that moment.
Okay.
But what you were seeing in that moment was the electron hitting one atom in the screen. And then because of this collision, light was liberated. And then that light, at each pixel, you had a different electron and a different creating an image at the end that was moving with time.
Okay, and every projector does that, or no, right now, or they do it differently?
Right now, LEDs, which are most of the screens are.
But the projectors, they use it in the theaters for the movies.
No, because I think that cathode tubes are not used anymore, so it's a pity.
It's a different thing.
Because you could play, if you get an old one, you can.
No, I want to.
You can put a magnet close to it, and you would see that the image is moved, because electrons are sensitive to magnetic fields as well, and they are attracted to the magnet or deviated by the magnet. So you could play like with a magnet. You could by moving the magnet, you could change where the electrons end up in the screen, and thus change the image or deform it.
Wow. Okay. Sorry. Let's go back I feel like we can talk about for hours. I really still need to understand, and if you want to explain this one as well, I don't know, because you said it's almost the same as this, no?
Yes.
More or less. Okay. So, but the empty space, going back, because you said, and I love that the electrons can never exist in the same place. So nothing is empty because of that. Mm-hmm. So empty space is really an interaction of the electrons all the time, a constant interaction. But what I heard is that the atom itself, so within the electron, and the nucleus and the protons and everything, so the composition of the atom, there is empty space in there. Is that true?
I think
no.
not completely. I mean, it's true that both electrons and the nucleus are very small, so in that sense it is empty, but
because it's so small that it's empty?
Yeah, it's in a way it's similar to the solar system that we said, no? I mean, is the solar system empty? Yes, I mean, most of it is empty space, no? Apart from the planets.
Oh, okay.
There is nothing.
The universe.
No,
okay.
in between the Earth and the Sun, there's just Venus and Mercury and a few asteroids and nothing else, no? Mm-hmm. So in that sense, an atom is similar to that. There's an electron, there's the nucleus, and there is nothing in the middle.
But is it really nothing? Is it like, how is it nothing? And why is it nothing?
It's nothing because again, in fact, that electron is attracted to the nucleus because it's positive, negative charge.
Yes.
And if it's not falling into the nucleus, it's because it's moving very fast, orbiting like a planet. Why doesn't the Earth fall into the sun if it's attracted to the sun? Because it's orbiting, it has speed that at the same time the sun is attracting it, but the speed tends to make it go away from the sun, and then we are in an orbit that is a compromise between the two. I mean, if we had a little bit more speed, it would be like a comet, and we would go through the solar system and go away. And
that's the electrons also being repelled against the...
I'm just making the analogy of what would happen, like that that like the solar system is a balance between this speed that the planets have and the attraction of the sun.
Okay.
That
makes sense. My question, sorry, is just like, why is it a circle and not like random and chaotic or a square or a rectangle around the sun? You know, it could be or like this or because the atoms is like that, right? Like
the problem with the atoms is that they don't follow these classical laws of motion. They are called classical because they were discovered before by Newton and other scientists. But in a way it's similar, and in a way, as you say, it's chaotic in the sense that they don't have one defined orbit. So like an electron is not doing an orbit like the Earth around the nucleus. That's true. Okay. And that's because at the quantum level, where electrons live, they don't have a position that is well determined. And they don't have a speed that is well determined. And that's fundamental. It's not like we cannot measure it. It's fundamental. So that's why you have to think of it as a cloud, because you cannot know where it is, the electron.
And it's dependent on what
but it's still
factors then, if it's not a set speed or a set...
okay, then it's not random. Okay, it's not well defined, but there are also equations of motion in the same way as Newton could calculate, or the scientists now, they can calculate at what speed they have to send a satellite so that it stays around the Earth. They can do it, and they do it every day. Mm-hmm. No, every day you have new satellites going around the Earth. So it's easy to calculate. If you give it too much speed, you will lose it. If you give it too little, it will fall again to the Earth. So electrons do follow some laws of mechanics, but they are not. So they cannot be anywhere. They will also follow like an orbit where they are, but this orbit is not well defined. I know it's very difficult to grasp because we live in this macroscopic world where these quantum laws do not apply, so we cannot get an intuition of how it feels, right?
Yeah, it's really hard.
When you work a lot, you end up being used to it, but not fully understanding, right? I mean, there's no way you can really understand it conceptually because there's no analogy. So there are some things that are analogies, like the planets around, but in reality, it's not like this fundamentally.
Okay. So sorry, I asked you just because...
No. Of course, it's something
Should I think about it like that? Okay, so it's an analogy just of the movement, not necessarily of the form of...
Yeah.
Okay. All right. Wait, is it...
But...
Yeah? No.
It's true that these laws of motion of the electrons, mm-hmm. which are not real orbits, tell us that they are spherical. So they don't have any shape.
Okay, so yeah, I remember you saying in the beginning. So this is one of the few things that it is indeed. Okay, all right.
There are like different layers, and each of these layers with its own characteristics, but it's essentially spherical.
Okay, and it just goes across.
Yeah.
Okay, all right, and
it makes sense, no? Because if you are if you are a nucleus, then everything around you looks the same, no? I mean...
If you are a nucleus, everything around
you're alone,
yeah.
And then you see electrons around.
Yeah.
So if we had any other shape that was not a sphere, there would be like some preferred direction. If it was a square, why should there be a vertex on that edge and not on this one? No? I mean, I am a nucleus. All the electrons are the same around me. There is no preferred direction. You see what I mean?
See, so the sphere basically englobes.
The sphere is completely symmetrical. It has no special...
Doesn't judge.
Doesn't judge, yeah.
Wow.
Whereas if you were like a cone, you would have a point. And why should there be a point in one direction and not in another? So the sphere is the most symmetrical without any preferred direction or any preferred anything. So here, if we are in the middle and we look around, we can see that somebody, an architect, designed this to have walls in one corner. But if we were to throw bricks around us at random, you wouldn't build this. You would build something that would be roundish, right? No, if you throw bricks at random.
You think? I mean, you know, probably.
You wouldn't build. Of course, you wouldn't build anything. But the bricks that would fall around,
it would always
be around, you know,
wow.
a circle more or less, unless you really point in a given direction.
Oh,
if
because they follow the law of the physics of the atom, so they would fall.
Because there wouldn't be any preferred direction, no? If you're doing it close at random, blindly, why should you point in a given direction?
That's so interesting.
So that's why also a nucleus does not have any preferred direction. So electrons around it, and the electrons, when they see the nucleus, they see it wherever they are, they see it the same way.
That's really beautiful, because I don't know if you know, but the masculine energy is represented as a vertical energy, and the feminine as a circle.
Cross.
That's what I heard from a shaman that I really like. I'm really into those kind of things, that the representation of the feminine energy is always circular and the masculine pointing. So I guess it goes to the essence of the atom, because the nucleus is circular, right? Spheric, a sphere, and the electron kind of points it, like you were saying, and kind of gives it the direction.
Okay, yeah.
A perfect combination of the two energies. I don't know. This is my mind making an assumption, but I don't know if this is correct.
Well, it's a bit far-fetched, but you could think of. I mean, at the end, sometimes the problem is that what we call energy is a different idea of what a shaman could call energy, right? So in science, when we say energy, we mean precisely the interaction between a positive and a negative charge, whereas a shaman may have a more holistic view of what is energy. But there may be some coincidences.
But you don't think it's the same? I think it's the same. It just gives it a different.
Okay, but then why should male be electron, or what would be a non-binary person?
Okay, so you're saying, I guess then
I'm saying that
labeling it. So maybe we can change female to electron and. Or
no, I'm saying that you can make an analogy, but that it doesn't have to hold for all the cases. No, that you can have non-binary people, but you cannot have non-binary particles. They are either, as far as we know, they are only electrons and protons and nucleus in the nuclei.
They're always a combination.
They're always what they are. They cannot change, whereas we people can make the choice.
The choice. But I think even non-binary people, I don't know, but I think they also know that everyone is a combination of those masculine and those feminine. It's just a matter of which one you have more.
Okay.
I think this is where the shaman is coming from, and from what that everyone has, but because you maybe were born or raised in a certain way, or your body is more inclined to that, maybe you have more feminine or more masculine, but everyone has that, and that's where I was coming from, that maybe those energies come from our feeling that we cannot perceive, or we cannot see, but of the atoms all around us, because our bodies are also atoms, right?
You are atoms.
One stomach has a lot of atoms. Wow. Okay, and once again, sorry, we're going to keep going back to this. So why does the scientific world, or why has anyone called it empty, and why is it empty so that this relationship can happen between the electrons and then the protons, or is it do you know what I mean? Is it empty so that these energies these connections can happen, or this negative repel can happen, or is it really, I know now from this conversation that it's really not empty, because nothing is really empty, but if within the atom there is nothing between the nucleus and the electron, then it is empty within the atom.
Yeah, but at the same time, the electron cannot get closer to the nucleus than what it is. So it's empty, but not that empty. I know, I mean, what I'm trying to convince you is that this concept of emptiness is relative to what you are probing that thing with. You see what I mean?
Yeah.
I mean, like I said, no, I think maybe gas is the closest analogy, no? So this room seems empty, or air, because we don't feel the air, but if I was a butterfly flying here, I would feel the air a lot. So probably it would feel like swimming, and it wouldn't feel like an empty room, because being a butterfly, being so small and needing the air to fly, I need to feel the air all the time. So I don't think it's empty. I'm swimming in the air, probably, no?
Okay.
So a butterfly would tell you, no, it's not empty from here to there. If it was empty, I would fall. There's air in between that I need.
And the air is...
So going back to the atoms, whether it's empty or not depends a lot on how you try to poke it and say, hey, how are you? Right? Because no, because that's what scientists do, and they do it in very different ways. No, like we can throw light into things and see how it responds. This is how we see things, but also how we see smaller things. But we can also throw other electrons to it, or we can mix with other matter and things like that. And again, if you were a neutrino is a particle that is created in the sun.
Okay.
And it has no charge, and it's neutral. So it wouldn't see an atom. It wouldn't
no charge is like not positive, not negative.
No positive, no negative.
It's like, okay.
But it's not light.
What is it then? It's so hard to imagine it. Is it?
Yeah. Well, it's
a bacteria.
No. It's like a little bit like an electron.
Okay.
Without a charge. But
So
the electrons are kept electrons are kept in the atom because they are attracted to the nucleus by the negative positive charge. And they see other electrons because the other electrons have negative charge. So if you don't have charge, it's as if the electrons are talking to you, but you don't have ears. You cannot hear it. So there's nobody. Can you think a little bit like this? So imagine an atom like people talking to each other. This is what interactions means, no? For us, no? Mm-hmm. And then you are blind and deaf, without hearing, and you walk around, you would think that it's empty. There's nobody, because you cannot interact with anybody.
Okay, you cannot. Okay.
So for you, that space, that room is empty.
But that person could still feel.
Yeah, because then you would be interacting. But the poor neutrinos cannot feel almost anything. So for them, everything is, even the whole Earth is empty. And 99% of them go through the Earth. They only interact from time to time with the nucleus. Very rarely.
When is that time? What
I don't know, because that is really a part of physics that I'm not familiar with. I know about it, but so there are huge detectors that try to detect the billions of neutrinos that go through them. From time to time, they can catch one.
So empty space is a matter of perspective of whether
exactly. That's
you
why,
are looking from
that's why,
an electron or the nucleus or this one that you just told me. What's the name?
Neutrino.
The neutrino. So it's all a matter of which particle you're looking from.
Yeah, and at the end, it's a matter of how strong you're interacting with that person. Again, we can make the analogy of the sound. Mm-hmm. If you speak very quietly, and I walk at 4 meters from you, I may not hear you.
Correct. Yeah.
Right? So, and for me, then that space is empty. There's nobody. If you're shouting at the same distance, I would hear you, and I would know there is somebody, and I could come to you and talk to you. So how strong you're interacting, it also feels how empty you are or how not empty you are. If the interactions are strong, then it feels as there is a lot of things around there. If people are shouting, it feels there's more people than if people are talking very quietly.
Okay. So that could be a way to understand the empty space around the nucleus and around.
Yeah.
Okay.
So for an electron,
okay. That makes a lot of sense.
inside an atom, they are all shouting very strongly.
Loud,
so
like screaming.
Loud, they are screaming. So if I'm an electron around here, it's like, whoa, there's a lot of people, big party here. Okay. I'm excluded from here.
Like a concert.
Yeah. So it's a concert that is booked. So no place for me. Right?
All right. And then you go somewhere else.
And I would rebound and go somewhere else.
Oh, wow. Okay. See, like that, I understand. All right. And then going back to the beginning, I think for me is the last question, because this is so much information. And thank you so much. It's one of the things that I have already in the video, and I will send it to you. Sorry I didn't, is that I'm also trying to connect, Schopenhauer, the philosopher.
Yeah.
He talks about the world of the will. And I thought it was so interesting because he was saying that we are constantly in this loop of the will. And I thought that there was a connection to how the atom also behaves with the electron around the nucleus. So, but then you said, I think, if I recall correctly in the beginning, that the model of the atom is not really correct, the one that we have, that has the nucleus in the middle and then do you know what I'm talking about?
It's not orbiting, like we said, it's not going round in the way that it's because of this quantum properties of the small things, it's blurred. So you cannot know where the electron is. And that's why at the beginning you have to think of it as like a cloud around, a cloud of, it's not a cloud of electrons. In fact, the electron is somewhere at some point, but we cannot know where it is.
What does it look like when you see it in the microscope?
When you see it in the microscope, it looks a bit like this, but you're not seeing a single electron. You're seeing the whole thing for a given period. But if you could throw a single electron to a screen, then you see just one point. So it's true that they are points.
What color?
Oh, that depends on what it hits. The electron itself doesn't have a color because only light has colors. So, but when it hits something, the electron, that energy will be released as light sometimes. And then, depending on what it hits, it will release color from different.
Okay.
It will release light from different colors. So what is strange, what is almost impossible to believe, but this is what apparently all the experiments have proven, is that I generate an electron here, I measure when it hits the screen there, but I cannot tell you how it went from here to there, or what is the precise path that it followed.
Okay.
You would think that it would follow like a line or something. No, not. There are many experiments, and it would take us very long.
So they could go 100 kilometers up, down, up, down, up,
well, in
down,
fact,
and then.
No, because I can tell you what's the probability that it went around here, and it would be almost zero that it went through the next floor. Okay. But I cannot pinpoint what's the exact path.
Okay, if you went through the camera or if you went through
Andreas. But I can tell you that 99% of the time, or of 99% of the electrons that I throw, went through this region. But I cannot tell you whether one particular one went on the right or on the left of the camera. I have no way to telling you this. And this is not because I don't know how I throw them or something. This is because this property that for us is so common sense, where is it? It's not well defined for an electron. So its position, it's not well defined. Yeah, I know it's almost unbelievable, no? But
Oh, wait, I'm going to check something. Oh, good, ¿todo bien? Sí, es la luz. ¿Qué está? The light changed a lot,
Yeah.
so I'm just going to change it here a little bit. Okay, so I don't want to take too much of your time.
Yeah.
It's going to be my last question. Thank you so much. I have a billion questions in my mind, but I could go on and on. Si quieres hablar un poquito en español o català?
En català, sí.
Una miqueta en català. És que meu català és...
Tu pots parlar espanyol i jo parlo català, ok?
Ok. M'agradaria molt parlar català perquè jo tinc, com te ha dicho, una parella lingüística hace 3 mesos.
Jo m'he apuntat de voluntària, ara, però no tinc parella lingüística encara.
No, i és molt, molt, molt interessant, però amb ella parlo tot, i per altres persones és com, què... Però,
no, tranquila. Parla castellà.
Ok, la última cuestión, quizás sería también un poco para el instituto y un poquito ayudar, y también una cuestión que tengo yo como persona normal, ¿dónde está yendo las investigaciones que hay en el mundo? ¿Cuáles son las cosas que se puede... otras palabras, nosotros sabemos mucho, pero no tanto de la composición, hay mucho para descubrir, básicamente, sobre todas estas interacciones y lo que pasa en el universo, en el mundo y todo. ¿Hay algún percurso o algún camino donde todos los cientistas o físicos o químicos que están intentando descubrir, o una cosa que es la más importante ahora de intentar entender, o una relación que, yo creo que hablaste de esto en el inicio un poquito, que se está intentando entender, que podría quizá nos dar una mejor comprensión de nosotros y de cómo nosotros nos interaccionamos uno con los otros como humanos, también porque estamos en un momento muy casi débil de la humanidad, que yo creo que tú por tener una, perdón, digo tú, no, usted,
tú,
¿verdad?
Tú
Por tener un estudio tan profundo de lo que es la creación, lo que es el mundo, lo que es todo, y también un poquito lo que pasa con mi serie, es que yo creo que uno de los problemas del mundo es que no tenemos conversas profundas suficientes. Es todo muy superficial. Y es en la superficialidad que vienen los confrontos. Cuando es profundo,
sí,
miraríamos que todo lo que estamos hablando es total nonsense. Entonces, ¿qué es que te enseño estas cosas bonitas y lindas sobre, no sé, sobre nosotros, o un poquito donde... Creo que entiendes lo que estoy intentando decir.
Sí, mira, és veritat, i justament crec que una cosa que et dona el ser científic i l'estudiar coses complexes és adonar-te que les explicacions simples i superficials moltes vegades, diguem, que es donen fake news i que es donen acostumen a ser falses. Bueno, les fake news són falses sempre, però o sigui, si els àtoms són complexes, els humans que estem fets de tants milions de milions d'àtoms som encara més complexes, no? I aleshores intentar, diguem, promoure solucions trivials a problemes molt complexes de la nostra societat, des de la immigració fins al canvi climàtic, fins a, no ho sé, les relacions entre nosaltres, acostuma a ser una forma fàcil, potser, d'aconseguir vots, una forma fàcil de transmetre una idea que potser és molt fàcil que qualli amb un tuit o amb un missatge d'Instagram, però que quasi sempre hi ha molt més que no el que surt allà, no? I quasi sempre les solucions trivials i fàcils no acostumen a ser les que porten a una bona solució. I jo crec que això és una cosa que, encara que sigui molt diferent dels àtoms, però que, bueno, fent ciència t'acostumes, com a mínim, i a plantejar-te que no hi ha dogmes, que tot pot ser qüestionat, no? I que bueno, això, que val la pena fer una segona volta a allò que t'han explicat i allò que tu saps, perquè potser no és veritat. I potser hi ha un experiment que demostra que el que tu et pensaves no és el que et pensaves i ho has d'acceptar. I això també serveix per les relacions entre les persones, no?
Una constant qüestionar de tot.
Bueno, jo crec que ens serveix bastant per això. Una mica d'escepticisme és bo. Massa potser no, però també s'ha de tenir una mica de fe en algunes coses per tirar endavant, però també una mica de distància i dir, bueno, a veure, parlem-ne, no? I si no és així? I si hi ha una altra explicació a darrere? I si això estaria bé que la societat s'ho apliqués en general?
I creus que aquesta como equilibrio de así y así está presente en el átomo?
Bueno, els àtoms pobres són molt simples. Bueno, són complicats, però al final com veiem els àtoms és més com nosaltres els volem veure, no? Que no com són, com seria un àtom sense els humans? Sí, és a dir, podem entendre un àtom només fins al punt que nosaltres podem
entendre nosaltres.
Sí, fins al punt de com funciona el nostre cervell, no? O sigui, no sé com una altra intel·ligència podria entendre un àtom, no?
Doncs los átomos que nosaltres coneixéis, és tot una quasi reflexió de que nosaltres coneixem de nosaltres.
Bueno, no. Tota la ciència intenta interpretar la naturalesa, però és una interpretació a través de la nostra visió que tenim, dels nostres coneixements, de la nostra manera d'interaccionar amb aquesta naturalesa. O sigui, no existeix.
Pot ser que un alien lo interpretaria totalment.
Bueno, hi ha unes coses que, si fem el mateix experiment, sortiria el mateix. Aquí hem d'estar d'acord. Però potser ell podria veure unes coses que nosaltres no podem veure, o potser ell podria pensar un experiment que nosaltres no podem pensar, i aleshores descobrir coses que nosaltres encara no hem descobert.
Doncs hay espacio, com es diu, hay espacio para molt més.
Sí.
Adentro d'un àtomo nosaltres podem venir a descobrir molt més.
Sí, al final tot estem fent d'àtoms, per tant tot acaba depenent de les propietats d'aquests àtoms, no? Fa molts anys que els estudiem, els sabem.
I és possible que en 10 anys,
sí.
No sé, una altra persona va a descobrir que una part, un altre nucli o un altre...
Bueno, això també a vegades m'agrada com aclarir-ho, perquè tot i que la ciència sempre s'ho qüestiona tot, no vol dir que no hi hagi coses que estiguem quasi segurs que seran d'aquesta manera i coses que encara sabem molt poc. Aleshores, fa molts anys que estudiem l'àtom i sabem bastant com és. Ningú vindrà i ens dirà que és completament al revés del que ja sabem, però algunes coses, com per exemple com els neutrinos interaccionen amb els àtoms, això és una cosa que no sabem. Però els electrons els coneixem molt bé, fa molts anys que els estudiem. Els nuclis també els coneixem molt bé, però encara no sabem com fer-los fusionar entre ells. És a dir, falten coses per saber? Sí, però també n'hem après moltes.
Moltes mercès. I don't know if you have this was a lot. If you have any questions, if you want to ask, I don't know if you understood. Wow, this is like still going. I don't know if there's any part that you thought like, oh, that was so weird. Oh, I wish I knew more. No, if not, it's fine. It's fine. I know it's a lot, but just maybe.
I think they are overwhelmed.
Yeah.
One experiment that we did in the past that separates the nucleus from the electron is the nuclear bomb. When you have the nuclear bomb, you separate the nucleus.
When you have the nuclear bomb, you I told you that this new kind of energy is nuclear fission, which means putting two nuclears together. The nuclear bomb is based on nuclear. Sorry, I said this is fusion, putting them together. Fission, they could have chosen different names. Fission is when you break apart the nucleus, and that also releases energy.
Like the sun.
The sun relates. No, the sun is mostly fusion. So putting atoms together. Whereas the nuclear, they're also like, but all this energy comes from nuclear energy. But the nuclear bomb is mainly by breaking apart atoms of uranium or plutonium. You've heard about them. There's no uranium and plutonium in the sun.
No.
The sun is mainly formed by hydrogen and helium, which are the simplest atoms. One electron, one proton. That's hydrogen. So you cannot break that apart. But two hydrogen atoms can go together, join together to form one helium atom. And that's what releases the energy from the sun and what keeps us alive.
Wow. So, did this answer your question? I lost some part of it.
No, I was confused because he explained the difference between a fusion and a fission.
Yeah.
And what I was saying is a fission.
So big atoms, huge ones, like uranium, that have, I don't know, maybe more than 100 protons and neutrons, they release energy when they break apart.
Okay.
Whereas other atoms, like the small ones, they release energy when they come together, like hydrogen.
And why is that?
Too long.
Too long of an explanation. But like this is the opposite interaction.
Because there is like an optimal size of the nucleus. And so if you're too big, then you release energy by becoming smaller. But if you're too small, you release energy by joining and becoming bigger. So there is like, I think the most stable nucleus, I'm not sure, but I think it's the iron atom, the nucleus of the iron. So if you're lighter than that, then joining together will release energy. But if you're heavier, by breaking apart, you will also release energy.
Okay. And I guess that releasing of the energy is what I understood from this conversation. When you talked about the butterfly of the empty space, it was so beautiful. Maybe that's why it's not empty, because every interaction is releasing energy.
Yeah,
in fact. And so the empty space is not empty, but it has to be empty so that that energy that is the reflection has to be there.
Very true. In fact, we didn't go into that, but electrons and protons interact by exchanging photons among themselves. So there is something in between, and that's what keeps them together. So and these photons are the energy, right?
Okay. So it has. So I guess my question here today was, why is it empty? Why does it have to be empty? So you just explained to me that it has to be empty so that relationship can happen.
Yeah, there are many things that are happening in
otherwise, that wouldn't happen like that, because it would have other things.
Yeah.
Wow. Okay. Yeah, that does make a lot of sense. And the last one you said, the relationship was, it's just so many names: electrons, the protons,
and the neutrinos.
Neutrinos. Okay. So you said the neutrinos now, right?
Yeah.
That they also in this relationship.
No,
No.
photons.
Oh, okay.
Photons are like the particles that compose light or light.
Oh, that's
Sorry?
right. Those
Without charge.
Without charge.
the
right.
ones that have no charge. Good. Gracias.
But then this
sí.
complicates a lot, because I was telling you that electrons do not see photons, but in fact they do see them a little bit from time to time, and so
Another thing is like sound. The sound, you don't feel it, you hear it, but the sound travels around.
Yeah.
The most atoms, it's an oscillation on the thing, so you hear.
Yeah. Sound is like pushing atoms.
Yeah.
And then that push translates and propagates from here to you.
But the sound itself is also an atom, no?
No. The sound is
So
like.
what is sound?
Sound is
Oscillation in a simple, en español, es una oscilación en una línea. Si vos tenés,
Bueno, en todo el espacio.
Sí, en todo el espacio.
Sí.
Una línea como para decir.
Pero si no es un átomo, entonces lo que es la composición del sonido,
El sonido. No
física y químicamente.
No, el
¿Entiendes?
sonido es...
Una vibración,
sí.
pero no tiene forma de... ¿Entiendes? No tiene núcleo, no tiene materia.
Se propaga, o sea, la materia se propaga por el aire que está hecho de átomos, se crea en tu boca que está hecha de átomos, pero las vibraciones, lo que produce el sonido no es el átomo en sí, sino el hecho de que este átomo vibra, entonces me pasa la vibración a mí, yo la paso.
El sonido cambia en base a la temperatura también, por ejemplo.
Sí.
Si la temperatura es muy alta, el sonido puede variar el pitch.
Entonces es una consecuencia
y
de un
el-
átomo, básicamente, el sonido. Perdona, eso, para entender.
Bueno, sí, todo es una consecuencia.
En el vacío no podría, por ejemplo.
En el vacío no hay sonido. ¿Habéis visto esos experimentos que ponen un despertador en una campana y van quitando aire y llega un momento que no se oye? Porque está vacío, entonces no se pueden propagar las vibraciones desde el despertador hasta fuera.
Okay.
Eso pone una cosa con-
Y no habéis probado, eso es muy... Lo tenéis... ¿No habéis probado de hablar, de comprar un helio?
Sí.
Ah, sí, claro, en la...
Interfiere la voz.
Claro, el helio es más...
balón, ¿se dice
Sí,
español?
en
Balón.
un globo.
Globo, balón es portugués.
En un
Inglés.
globo de helio, el helio es mucho más ligero que el aire. Y como es más ligero, se mueve más rápido. Y como se mueve más rápido, tu voz suena más aguda. Porque...
Ah, es por eso.
Sí.
Entonces
El
más...
sonido son una cantidad de ondas negativas y positivas sobre una línea que entra en la oscilación. Por ejemplo, 440 veces entra, sube y baja
Sí.
En un segundo o en un metro.
Sí, un segundo.
Un segundo para hacer la nota 440 en la. El la
Pero
es-
más agudo es más vibración.
Más vibración.
Entonces,
Doble.
como el helio es muy ligero, vibra más rápido. Eso es fácil de entender. Un ejemplo, una pelota de ping-pong
Sí.
salta más rápido que una de tenis, ¿no? El movimiento es como más lento. Pues los átomos de helio vibran más rápido y por eso sonamos más agudos. Sonamos con esta boca así.
Okay.
Porque hacen que ellos vibran más rápido.
Wow.
Hay un gas, por ejemplo, que es mucho más pesado, pero que es muy difícil de conseguir fuera de un laboratorio, que hace lo contrario y hace que
Tu voz.
tu voz sea muy grave.
¿Es de los gases naturales o unos ya inventados después?
Es sintético.
No, sí.
Ah, es
Sí,
sintético.
es
Es por eso que no es tan fácil de...
Por eso no es...
¿Y tiene como consecuencias malas para la salud?
No.
No. Ah, ok. No
Tiene
sería
consecuencias que cuando lo inspiras, como pesa más, tarda más en salir de tus
ok.
pulmones, porque se queda debajo, claro.
nada. Entonces no es como el helium, que es como una cuestión de segundos.
Sí,
sería
no,
mucho
claro,
más
dura un
tiempo.
poco más.
Ah,
Porque el
wow.
helio enseguida flota. O sea, el helio, como pesa menos que el aire, sube y se va. Cuando tú respiras enseguida, cuando abres los pulmones, él sale enseguida. En cambio, este se queda como más ratito.
Ah, wow. Wow.
Hay experimentos también que puedes hacer flotar, puedes llenar una piscina con este gas y como pesa más, se queda debajo, no ves nada.
¿Cómo se queda debajo? Perdón. Creo que no
Imagínate
entiendo eso.
una pestera,
Sí,
¿sabes?
sí, sí.
De cristal,
Sí.
para ver a través. Entonces tú pones gas, tú no ves nada, pero se está se está llenando de gas.
Sí.
Entonces está aquí llena de gas, pero como pesa más que el aire, no va a salir. Y entonces puedes poner un barco de papel y flota. Porque es más denso, porque es como agua. No es tan denso como agua, evidentemente, pero es más denso que el aire. Y entonces el barco flota. Os puedo mandar un vídeo si queréis.
No, qué cool. No, estoy pensando que nosotros podríamos fluctuar si estamos arriba de un aire muy denso también.
Pesamos demasiado.
Estamos demasiado claro.
Tienes que hacer un barquito de papel muy
Sí,
ligero.
pero si es mucho gas, sería posible, ¿no?
No, porque siempre
No hay
es un
ninguno.
gas. No
Ah.
hay ningún gas que sea más denso que tú, que eres bastante
La
hecha
que-
de agua, básicamente. Eres sólida y líquida. Entonces no hay
Oh.
ningún gas que sea tan denso como esto. Pero podrías hacer un barquito suficientemente grande y ponerte encima, quizá. Pero
Grandísimo.
grandísimo. Sí, porque cuando lo ves realmente, o sea, das un golpecito y enseguida se hunde, pobre. Pero es una sensación muy rara verlo flotar encima de algo que no estás viendo.
Eso sería
Porque es un gas, además, que podría tener color, pero es un gas incoloro. Entonces,
¿Y ese gas es difícil de obtener?
yo creo que sí.
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 Que es una cosa así media rara.
Bueno, tendrías que comprar... Es que, claro...
No es como se puede ir a comprar y...
No. No.
Muy bien, chino, bueno, con un poco de
Y para... No, pero eso sería muy interesante. Yo hago mucha arte y sería muy interesante quizá tener una pieza de arte fluctuando con ese gas.
Ah, sí.
Arriba y abajo y
Bueno,
al
pero al
medio.
final es un gas, o sea que al final no dura mucho. O sea, se queda flotando
después
por
se
allí,
va.
pero con el tiempo... O sea,
Pero si es
se
un
mezcla
vacuum.
con el aire, poco, pero se va mezclando. Entonces lo
entonces
puedes tener,
después
no
se
sé
va
si unas horas o unos días, pero no puedes tenerlo porque al final se va.
Pero si es cerrado, si es un espacio
Sí,
cerrado
pero
también...
si está cerrado, no, claro. Si lo
mantiene,
tuvieses todo cerrado,
sí,
se aguantaría bien.
se aguantaría.
Sí. Aguantarían dos aire y este gas debajo. Podrías
Sí.
cerrarlo todo. Sí,
Sí,
eso sí.
exacto. Entonces no sería el topo, pero sería como el medio
Sí,
o algo.
sí, sí, sí.
Oh, wow, eso sería interesante. Vale, no sé si tienes alguna pregunta más, si entendiste más o menos qué es mi...
Sí, no, es muy interesante porque en nuestro día a día no pensamos estas cosas, ¿no? Vamos
Y
haciendo...
perdona que vaya con muchas preguntas.
No,
soy muy-
pero es interesante por eso, porque te hace plantear cosas y cómo explicarlas.
Sí, porque yo como...
Y a
te
mí
he
me
dicho,
gusta...
Me miro muchos vídeos, pero yo creo que ninguno está abierto suficiente para una persona como yo,
Ya.
que yo entiendo las cosas muy mágicamente, muy como las historias, tiene
Ya.
que ser, si no, para mí no tiene sentido. Y creo que me ayudó mucho tener toda esta conversación.
Muy bien.
Pues, muchas gracias. Te envío todo, claro, al final. No voy a hacer todo.